Okay, so our next speaker is one of our organizers, Professor Liu Shen. She is also from EECS department from University of Michigan. Before that, she received her PhD from electrical engineering in Stanford, and prior to that, she received her bachelor degree from Tsinghua University electrical engineering department. Before joining Michigan, she spent 1 year as a postdoc at Harvard Medical School, and her major research interest is in biomedical AI, diffusion models, computer vision, signal and image processing. And today she will talk about something about using diffusion models to solve general inverse problems. With further ado, let's welcome Liu.
Okay, great. Thank you so much for the introduction, great, by Chin. And thank you so much for everyone attending the talk today. And I'm very happy to share on some of our recent works on using the diffusion model for solving the inverse problem. So we have seen pretty great talks about the different aspects relevant to the diffusion model or more generally generative AI models. And it's also very nice, like Renee touched on something for the medical applications in the disease diagnosis, the image classification in the last talk. So it's a great pleasure to share with you more specific in this particular domain for the biomedical imaging applications and how AI can be helpful for this domain. Okay, so firstly, as we have seen over the past few years, how the AI is changing make a big difference in a lot of applications in the real world. And until for 2 or 3, 5 years ago, when we see this generative AI model has been introduced, as especially with these ChatGPT models that really make the AI come into the life for everyone. And beyond these applications we have seen, so in this other specific domain for the biomedicine and healthcare, AI is also playing a very big role to make a huge change in many applications. For example, the disease classification, the protein structures, and patient healthcare. And there have been a lot of news we have seen every day to say how biomedical AI has become an emerging and expanding areas in both the industry and also the academia. So with all of this kind of the attention attracted from the different researchers, so we can see why we care about this domain and why this domain can give us some the new insight is because could be helpful to leverage AI as a tool for us to understand the human health at the different levels. This can also come into many different applications at the various levels. And this is actually set up the foundations for the research of my past few years and also the research in my group with my students as well to see how we can leverage or develop the efficient and advanced AI models for the different biomedical imaging. This including how we can use AI to help with the medical imaging, which it means to say how can we get image information from the human body to illustrate internal structures. It can also be helpful for how can we leverage or advanced AI technique for solving the biomedical data understanding problems, in the disease diagnosis or segmentation or other processing. So for this talk, I will mainly focus on the AI for the biomedical imaging, and also to show you how the generative AI specifically can be helpful for this task. For the audience who may not be so familiar for the biomedical imaging, I will first use some time to give a high-level and a brief introduction about what is medical imaging and why we care about these problems. Hopefully, this can give you a general sense why this problem is important and how this can be relevant to the generative AI models we're looking into for the whole day of this symposium. So firstly, for the medical imaging, there are many different modalities or different imaging systems. I will give two specific examples that have been commonly used in our daily life. The one is the X-ray computed tomographic imaging. The physical fundamental behind it is that we get the reconstructions for the human body at the projection for the different view angle. And we want to reconstruct the cross-sectional images for the internal structures of the living subject from those projections from the different view angles. And one important thing is that for the CT scanning, is that it will expose the human body or the living subject to the radiation dose. And in order to reduce the radiation dose in the CT imaging, we are usually trying to develop more advanced computational algorithms or model that could sample fewer projections while getting the reconstructed images in the good quality. So in this case, we could be able to help reduce the radiation dose in the CT scanning that will be very important for many clinical applications. And beyond the CT imaging, there is another modality that is also pretty important in many applications called the MRI or the magnetic resonance imaging. Similar to CT, we also want to use MRI to visualize the internal structures of the living subjects or the human body. But there are some different kind of the medical physics behind how we get the MRI images reconstructed. So which is actually to get the acquisition in the frequency domain or what we call always as a K-space in the MRI community. And for the MR scanning, it always takes a longer time that could be 10, 30 minutes, even to different several hours to get the whole MRI acquisition process, also with a different contrast. So always like in order to accelerate the MRI scanning procedures, we always want to develop more advanced algorithms to undersample the case-based data and also to reconstruct the artifact-free MRI images. So as we can show in these figures, so when we have like the different sampling about the different parts of the case space or the Fourier space, we could be able to get the image reconstructed with different information. But how can we do the sampling? How can we make these algorithms can give us more higher quality of the reconstructed images? So that is how the MRI sparse sampling reconstruction is trying to investigate. So overall, the motivation for us to care about the sparse sampling medical imaging, for example, in the CT, in the MRI reconstruction, is due to the reason we want to reduce the radiation dose, we want to reduce the scanning time, or there could be other things like to improve the spatial resolution or the temporal resolution in the MRI scanning with the dynamic imaging. So there are a lot of the reasons from the clinical, from the medical applications why we care about this kind of specific, what we call the sparse sampling medical reconstruction area. And if we formulate this more, a little bit like more in the theoretical or the engineering way, we can consider the medical imaging also as one of the inverse problems we're talking. So here, if we look into the imaging systems at the forward operator that is noted as the capital A here, and the images we want to reconstruct is the X, which denote the high quality images, and the Y is the measurements that we got, either the Fourier space acquisition for the MRI or the different projections for the CT imaging. Always there is some like the noise term that we also need to consider. So in general, this gives us the process like for our imaging systems in the forward process. And the inverse problem here is that we want to reconstruct the high quality MRI image, the medical image from the measurements that obtained or acquired in the measurements domain of the Y. And in order to solve these problems, even before the deep learning age, there has been so many conventional approach over the decades of the years has been paid attempt on solving these inverse problems from the statistical methods and also the compressed sensing back to 20 years ago. And in the recent years, after we have seen this kind of promising opportunities provided by the data-driven or learning-based methodology, people are thinking about, okay, how this could be helpful to solve this inverse problem that may even further push the boundaries of the conventional approach. So that comes to the motivation at a very early stage for the deep learning-based reconstructions. So as you can see in this kind of the figure on the right, so if we are looking into like the fewer projections for the CT images, which usually will need like thousands of the projections at different view angles in the clinical protocol. And if we have like more and more priors that could come with our reconstruction algorithms, there may be more potentially possible that we could reduce the number of the view projections to get the high quality reconstructed images of the city. And what kind of priors can be used, and also what level of the prior knowledge that can be helpful. So that comes to a generalizable or uniform lines of the researches, including the conventional and also the regularized reconstruction algorithms. And with the deep learning-based reconstruction, our assumption or our hope here is that if we could be able to learn this prior through the data-driven way, that could give us a higher level of the prior knowledge or a more powerful prior that could be able to solve this kind of inverse problem. So this comes to the key point I will first want to bring as insight for using the deep learning as a prior to solve the inverse problem. And then with such kind of the motivation, the next question is that how can we learn the data-driven prior, right? What kind of the deep learning methodology can be used? And also how can we make this kind of prior can be useful? So in this kind of line, back to the 2014 or 15, there have been the early stage work that leverage the deep learning based algorithms to solve the inverse problems, and mostly starting from the supervised learning algorithms with the paired data of the measurements and images to learning that. I will skip that part because it will take like a lot more time, but I will more specifically get into the part that will be relevant to the generative AI models in the topic of these symposiums. That how can we leverage the generative or the diffusion model to learn such kind of priors in the inverse problem solving? So as we have seen a lot in the previous talk from Mondi, from Chin, and also from Renee, so there have been a lot of like introduction about what is the diffusion model and how it can work to capture the data distributions underlying. So I will skip the most of the fundamental basics here. So we assume like, okay, here we have some diffusion model that could be able to capture the distributions as people have introduced in earlier talk. But I want to emphasize here with one thing is that it not only works for the natural images, it can also work for the medical images as well. So as you can see in this figure, if we consider the distribution will be the seed images from the different patients or different samples, it's also possible to use the diffusion model to capture the distributions across the different patients or across the population distribution in this kind of the unsupervised way, which means that here we're trying to capture the underlying data distributions without showing or without assuming any information on the measurements or the y there. And why this can be helpful, so one pretty great insight mentioned by our earlier speaker, Moni, is also, okay, we can solve the inverse problems using diffusion model as a prior by converting that into a conditional sampling or generation process. So that's exactly also the key insight at the very early stage by using the diffusion to solve the inverse problem. I will get a little bit more details here, like why this is intuitive and why this is useful by just showing this posterior score function. So as you can see from the base rule, we can connect the posterior equation or the posterior reconstruction problems as the probability of the x given y. So given the measurements, how can we get or how can we guess what the x should look like for our reconstructed images? And based on this kind of the theoretical computation, we can get the posterior score functions as shown in the second equation that will be relevant to two terms. The first one is about the score functions for the unconditional data distribution. So what is this? This is actually how the diffusion model is learning for the underlying distribution. And the second term is the PLI given X. And what is this? This is the Ford process. And in the medical imaging systems, we know what it is, like the CT or the MRI imaging process. So given this kind of thing, which means that, okay, if you want to solve the inverse problems, what we need to consider is information from both ends. The first one is the prior from the PX, and the second one is the PLI given X. So with this kind of thing, we propose our very first work in the 2020 to propose using the diffusion as a prior to solve the inverse problem. And for here, just considering the medical imaging with this kind of Ford process that including the physics-based transformation and also sparse sampling with the motivations we have seen from the applications in the previous slides. And in order to solve these inverse problems, our key insight is to convert this as a conditional sampling approach. So which means that according to this kind of combinations of the two terms, we want to combine this kind of information to give our outputs or the reconstruction Y by inject informations of the observed measurements from the Y into the sampling steps or sampling process of the diffusion models in this kind of the sequential generation process. So which means that our diffusion model is trained to capture the underlying distributions of the px. And after the training in the inference time or in the sampling process, we're trying to combine the informations of the py given x into this kind of process. And in order to get the posterior sampling or the conditional sampling to reconstruct the target image. And with this kind of the insight, I will not include all the details here, but feel free to check our papers, how we make the final optimization problems can work. But I will just show some results here to see like, it is pretty promising by using such kind of the unsupervised training or the pre-training diffusion model as a prior to solve it. It even can be comparable or even get like better performance compared to the previous supervised learning methods people has been used a lot to as the deep learning based reconstruction algorithms. And it's also pretty flexible to benefit from the advantage of using diffusion model as prior, because this kind of the capturing for data distribution, which make it can be pretty flexibly and generalizable to the different inverse problem solving at inference time. So for example, the different sampling pattern for the MRI or different number of projections for the CT images. So this has really benefited the practical applications for using this in the inverse problem solvings for different cases. And after that, we have seen a lot of works following up and also came out to trying to use this kind of the pattern, that is to solve the inverse problems for by using the diffusion as a prior. This could be like very general inverse problem solving, including the natural images, medical images, and also the other application cases. And the two main kind of the trend or the approaches people has been developing is how can we guarantee this kind of data consistency or the coherence with the measurements in this kind of conditional sampling or conditional generation process. So that is what we call here as the soft data consistency approach, which is mostly on the gradient at the different time state manifold, and also another series of the work trying to have the hard consistency to enforce the projections at the clean manifold to be consistent with the measurements. So I will not get into all the details for these papers, but I really recommend if you are interested in these areas, you can check those papers, like how good performance and how exciting those work are. But based on all this kind of existing work, we have also facing the limitations by using such kind of the diffusion-based inverse solver. So mostly I would say come from the computational constraints from the training and also the developing the diffusion model. For example, in the paper I just mentioned, the diffusion model requires a large number of the training data. Like in the CT MRI results, we need to train the model with like from the range from the 50K to the 300K to the images to get a single diffusion model. It's also pretty inefficient in the training time and also the sampling time. So which really requires like thousands or hundreds of the sampling steps to get one images. That could be like minutes or even 10 or 20 minutes for a single image. It's also pretty expensive in the GPU memory cost. That's also the reason why most of the current works can only apply to the 2D images and in the decent or the low resolution. But this kind of challenges make it pretty hard to apply this methodology to the real-world scientific or the medical applications. Because in the real-world applications, we are mostly dealing with the high-dimensional and also high-resolution images. So for example, in usually the standard CT imaging, that is the 3D volumetric CT, and with the standard resolution of the cube of the 512, it's very hard for the current diffusion models that can be easily adapted to this kind of the large scale of the data. And for the other examples, like in the MRI, we have the quantitative MRIs with a different contrast information. We have the dynamic MRIs that could be the 4D images even. We also have this kind of high resolution satellite images for the remote sensing that can contain thousands of the pixels at each side. So even though we benefit this kind of advantage from the diffusion-based model, but the current methodology is still facing the challenge and limitations to adapt to those real-world medical and scientific applications in these cases. So this really comes to our motivation. How can we develop or improve the efficiency of the generative diffusion models that could enable it can work for such kind of high dimensional and high resolution data? So this also comes to the key insight, the key problems I want to discuss in this talk, and also I will introduce some solutions we propose that could be potentially promising, and also I think in order to solve these problems, we are still trying our best efforts along this line. So again, to repeat what you just saying, and also to put that in this kind of paradigm or the graph here. So for the current work, if we consider these two dimensionality, one is about the model performance, the other is about the model efficiency, including the data, the time, and the memory efficiency. Most of the current works are focusing on how can we improve the model performance along these directions. For example, for all the works I just mentioned, pretty exciting, pretty good works, and also achieve really impressive performance to the 2D image problems. And there are also, with such kind of the motivation to improve the efficiency for the diffusion model, we have also seen pretty interesting works coming out, like the distillations of the diffusion, like the consistency model that can effectively to improve the time efficiency for the sampling process of diffusion, that can reduce the numbers of the sampling steps or the NFE as low as to like 1 to 4 steps. So this can be really cool, and also they have shown pretty good results for the image generation task. But how if this kind of the efficient model can be used for solving the inverse problems? So this comes to one of our recent works just accepted by the ECCV this year, that we're trying to use the consistency model with such kind of the good time efficiency to solve the inverse problem. And in this case, we want to be able to push the boundaries of the inference steps to 1 or 2 time sampling steps. And how can we leverage the consistency model as a prior? The key problem is that how can we get this kind of the data consistency with the measurements since we are not just doing the unconditional generation to generate any random image. We still want to the output images or generated images can be conditioned or constrained by our measurements information. So in this work, we're proposing 2 different perspectives of the constraint to inject this kind of the constraint condition information. The first one is the soft measurement consistency based on the control net. So by using the control net, we'll be able to adapt a pre-trained consistency model in the different tasks, different input, while keep the consistent model to be frozen or not need to be retrained. And in the other sense, in order to guarantee reliability for the consistency with the measurements, we also introduce the hard measurements consistency through the optimization that can make the output can really be consistent or coherent with the measurement. And through this kind of way, we can also be able to get this kind of the efficiency in the sampling time to 1 to 2 steps. So even though we have seen those kind of the works with like improved time efficiency in generation task and also the inverse problem solving, but I will to say like in the current works, some of the limitations are also faced by this kind of the methodology. So for example, in some kind of the tasks, we may compromise the model performance because we want to get this kind of efficiency in the sampling time. And in other cases, for example, in our work, we also need to retrain the control model in order to adapt to each task, even though it's efficient, but it's also not exactly the same as what unsupervised prior diffusion inverse solver is doing. So with this kind of the thing, the other kind of perspective, how for us to want to improve like the data and the memory efficiency is also what we have seen over the current works. So for example, like we just mentioned, if we want to adapt the current works to the 3D or even high dimensional data, we cannot really train the model on the 3D images because of the limited of the amount of the data or the limited of the GPU constraint. And there have been works proposed the very smart idea like, okay, we can use the 2D diffusion priors to solve the 3D imaging problems. And also by having the regression over the different slices to enforce these kind of consistencies over the other dimension. And this kind of works is also facing the limitations with the performance compromise, and also increase the inference time because you need to do the prediction, do the reconstruction slice by slice. So in all these kind of the existing works we have seen, we really want to get into this question, like if it is possible that we can improve the efficiency of the diffusion model, well, could be able to maintain the model performance in a good level. And especially if we can make this or enable it can work for the high dimensional and also high resolution imaging. So that's exactly what we want to pursue as our final goals in all this kind of research. So in order to solve this, I will introduce the two different variants of the diffusion models or the solutions that we propose that could be potentially promising to solve this problem and really enable the high dimensional inverse problem solving. So I will go these two sections each one by one. So firstly, again, as we just saying, for the current works, people have been thinking about, okay, let's use the 2D diffusion prior to solve the 3D imaging problems. And the insight here is also straightforward. We just do the 2D reconstruction slice by slice. And the other important component is that some regression terms will be required to obtain the cross-slice consistency in the other axes. So for example, here in the diffusion MBIR and also DDS work, it's using the total variation regression to get the consistency across the z-axis. But this also came to the limitations for this work from my perspective, because it will really depend on how large is how much weight is this kind of the regression terms, and how can we fine-tune this kind of thing versus the original training or the pre-trained models on the diffusions for each of the slides. So in order to make this can be more systematic and also more elegant way to enforce the cross-slice dependency or consistency, we propose this new algorithms called the diffusion blend, which is trying to nerd the score functions on the 3D patch. So what is the 3D patch here? You can consider it will be multiple slides across the whole 3D volumes, where you can adjust the score function to learning from the adjacent slices to make it can keep or incorporate this kind of cross-slice consistency. And by using this kind of ideas, so for example, when we are doing the training of the diffusion models, we will expect to see like the score functions for this slice at the next attempt step will not only based on the score functions of what it should be in the previous attempt step in the same location, but also can be relevant or get conditioned on the other slices in the other locations. So this really comes to the insight for us as algorithms. And if we expand this to the whole 3D volumes, so we propose this kind of algorithms to incorporate the cross-slice dependency and consistency that can ensure the entire 3D volumes can be reconstructed with a pretty good consistency or coherence in the z-axis without any handcraft regression terms. And here, one very interesting point is that we also include one relative positional encoding in our case to indicate like how separated and what's the distance between the slices when we are learning this kind of the cross-slice or multi-slice score functions. So this comes to the key idea and how does it look like in the results. So here I was showing the chronal values for human body for the 3D CT images with very high dimension that will be 256 times 500. So as you can see, like in the previous state-of-the-art results, which we call the DDS, even though it can get pretty good qualities in the XY axis in the axial view, but it's very hard for you to get this kind of consistency over the z-axis. So in this case, if we are using our diffusion blend algorithms, we can really see this kind of the consistency over the z-axis because we have this kind of the learning approach with the cross-slice dependency during the training and also with the position encoding. And we also got the comparisons and also conduct experiments for the ultra-sparse view CT reconstruction and also the limited angle CT reconstructions as shown in our papers. And especially we have observed a pretty large improvement to get this kind of consistency in the whole 3D volume reconstructions, especially with the consistency across the z-axis. So feel free to get into our paper to see a lot of like quantitative results there. And just to briefly mention, we also have another paper which is together with our collaborator, Professor Jeff Fislers in our department, within this kind of also ideas on the patch-based diffusion. But here, instead of considering this kind of multi-slice to the image slice as the 3D patch, we're considering the patches that can even go across the XY axis with the different locations in the image. And this is also very interesting works to showing like by learning the score functions on the patches with the position coding, it can also construct the score functions for the whole image and also can be used as a prior to solve the inverse problem. Due to the time limit, I will not include too many details here, but feel free to reach out and also look into the details in our paper. Okay, so this comes to the first solution I want to introduce. How about can we use the insight for the patch-based diffusion to solve the inverse problem and to make it can be more efficient for training, developing the diffusion model to get that kind of prior in the high-dimensional data. And beyond that, another thing that comes to our interest is about the latent-based diffusion and why this can be promising. So firstly, we have seen like how interesting and exciting results that we can get from the latent diffusion models or LDM. And especially it enables pretty efficient training, inference, and also the memory with the limited computational resources by encode or project the data from the pixel space, from the image space, into the latent space with a lower dimensionality. So the LDM, the stable diffusion papers have shown pretty good promising results for the generation, for the conditional generation. But this motivates us to think about if we could use such kind of the efficient LDM model for solving the inverse problems by using it as a prior. And in order to do this, one challenge we're facing is also how can we guarantee the data consistency with the latent diffusion model? Because you have like the encoder decoder at the beginning and end to connect the latent space and also the image space, while the measurements what we have is all in the pixel domain. So how can we get this kind of injection in the latent space to enforce the conditional generation for the latent diffusion in a reliable way? So this comes to our second insight. How can we make this kind of the high-dimensional inverse problem solving problem can be more efficient by using the latent diffusion model as a problem to solve this inverse problem? And in order to get the reliable consistency with the measurements or the data consistency, we propose this algorithms called resample that could be able to solve the general inverse problem, including linear and nonlinear problems, using this kind of the pre-trained latent diffusion model while data consistency. And the key point here is that no matter if your inverse problem is linear or nonlinear, because we have the nonlinear encoder decoder here, so your problems will essentially be nonlinear problems. So that is really, really challenging to have this kind of the data consistency guarantee. And how can we achieve that? So there are three main steps that we want to, we are trying to have this kind of consistency with the measurements. The first one, if we consider in this kind of latent diffusion space where we have like the ZT to Z0 to denote this kind of the sequential sampling process, in one of the sampling steps, if we want to inject information from the measurements or from the acquisition data, we firstly predict from the current time step manifold to the clean data manifold to get our estimated latent in a code which we call the Z0. And in this kind of case, we want to do the optimizations to really make this kind of the current latent code can be consistent with the measurements. So that is the second step, what we label as the optimization here. So we want to inject the information from the measurements of the Y into this kind of the optimization problems to make the current latent encode can capture information to be consistent with the measurements of the Y. And then it comes to the most challenging part that, okay, after we get this kind of estimation using the 3D formula, after we get the optimization, how can we get back? Because we need to get back to continue the sampling process for the sequential diffusion sampling procedure and to go to the next step and also to get this kind of the information from the pre-trained models for the prior, right? And in order to do this, we have tried the previous existing works on doing this, but we find like, okay, it's really unstable to get a reliable estimation to go back to the manifold at the time step t in a reliable way. So that is where we propose this kind of called the stochastic resampling methods, which is trying to project the measurements constraint latent code into the manifold in the time step t, and then to continue to the next attempt sampling process. And the key idea here, compared to the previous methods, is that we're trying to combine both the data consistency and the prior consistency. So I will use one formula here to explain what does that mean. So previously, if we're using the stochastic encoding process, we added the noise based on the scheduler of the alpha, and also to get from the clean latent code to the manifold and time step t. But here, in order to only consider for this kind of the process from only the Z0Y, we also consider combinations between the Z0Y and also the ZT from the last attempt steps. So that's exactly what we're showing here in this kind of the red box, where we're trying to combine these two samples, which is one conditional samples, and the second is the measurements constraint samples after the optimization. And by doing this, we're using the formula to combine the information and also a hyperparameter to balance the trade-off between these two parts information. And here, the green part shows the data consistency after the optimization to consistent with the measurements y, and the blue part means the prior consistency, which indicate the unconditional samples from the last attempt steps. And you can see, like, by changing the scales for this sigma t, if sigma t is close to the 0, that will be exactly just be the unconditional sampling. So which means that we do not inject any information from the y in this step. If the sigma will go to the infinite, that will actually go back to the stochastic encoding. So that means that we'll only consider or emphasize information from the optimization. So through this kind of the stochastic resampling process we propose here, that can be a pretty flexible way to balance the trade-off from both ends, and then to get this kind of the data with the low variance, and also can be able to continue for reliable sampling in the continuous or the consequent steps. So, okay, so this comes to the key point that we propose in this resample papers. And if you show, if you see that in the algorithms, so all the other things that is pretty standard and also like what people have been doing before in the diffusion-based inverse solver. And exactly this part, what I just mentioned, to get that kind of optimization in the clean manifold and then to project back use a stochastic resample is what's pretty interesting, and also the ideas we're proposing here to get this kind of hard consistency. And the results that we got from the resample is also pretty exciting. So firstly, for the experiments on the medical images, we're using the pre-trained encoder-decoder from the natural image datasets. And for the diffusion models, latent diffusion models, we also find and observe it's pretty efficient to fine-tune the latent diffusion models from the natural domain to the medical imaging domain using only thousands of the CT images. And in the previous work, there have been a lot of like the works working on the latent diffusion. So we are pretty trying to compare with the baselines, like using the DPS in the latent space, even though it was not designed for using the latent space. But for nowadays, with some like concurrent works as our resample papers, we have seen like more and more works get this kind of interest to solve the problems in the latent space. And we also have shown the results of the quantitative results to compare with the previous baseline in the different sites of the CT image reconstructions, and also for the natural image datasets with the different inverse problems, including the super solution, the impending, the deblurring, and also the other cases. So I will skip all the numbers here just for the time interest. So this comes to almost the end of my talk. Like, we want to say like, okay, it's very important for us to improve the efficiency for the diffusion model to make this kind of the new technique can be adapted to the high dimensional and high resolution image or data in the real world. And for our past research, we have proposed these two key ideas, trying to improve the efficiency by proposing the patch-based diffusion and also the latent-based diffusion to be as a prior to solve the inverse problems in the high dimensional case. And beyond that, I want to just briefly mention some other scientific applications beyond the medical imaging. So we have talked about medical imaging for a lot, but this kind of algorithms or methodologies is not only limited for the medical imaging, it actually can be used for solving many different inverse problems in the real world case, in the other scientific applications, and also even the inverse design. So just a brief mention two additional things here. The first one is that we apply this kind of the diffusion-based inverse problem-solving idea to the super solution for the satellite imaging, especially in the satellite imaging case where we have the trade-off between the spatial resolution and the temporal resolution. So how can we leverage the diffusion from the high resolution, trained on high resolution satellite imaging as a prior to give like more details on the low resolution satellite images that could be very helpful for many downstream tasks in the remote sensing. And here is the results that we got by comparing with the previous works, previous methods on the GAN-based approach, and also the diffusion set, which was also a pretty new paper last year from the Stanford people. And what's also more interesting is that for the satellite images, we also care about the high resolution data, right? Even though it's may only be like the 2D dimension, but we already care about how can we solve the inverse problem or the super solution for the high resolution satellite images. So this is one of the current works ongoing that we're trying to generate such kind of the high resolution 2D satellite images with like 766 68 pixels by each side, and also to solve the inverse problems of the super solutions in such kind of the large scale. And beyond that, we also expand this kind of idea to the other scientific and actually the physics applications with the inverse designs of the quantum photonics structures. So here is also the inverse problems that we are trying to solve. How can we design the structures of the quantum photonic structures to match or to achieve the desired physical properties instead of the conventional ways through the trials and errors at what people have been doing for many years? And we consider this as an inverse problems, and by using the diffusion to capture the underlying distributions as a priors for the structures, and then along with the prediction model to inject this kind of the desired constraint into the conditional sampling or conditional generation process to solve this inverse design problem. So just to give some examples to say like how these methodologies can be useful for many medical and scientific applications, and especially handling the real world applications. So finally, I want to thank you for all the funding support, my collaborator, my students who have been working, contributing for all the works I have mentioned in this talk. And feel free to contact me if you have any questions about the different works I discussed today. And also I look forward to any potential like collaborations. Thanks again.
Yes, I wanted to clarify for the first part. When you condition on the image Y, or the measurements Y, do you train a conditional diffusion model with Y, or do you use the 3D formula to approximate? That's the first part of my question.
Yeah.
The second one is, why restrict Y to be only the measurements? Why not be a segmentation or or the radiological report or extra information that would keep the anatomy?
Yes, yes, that's a very good question. So, firstly, for the first work, you mean the one we have? It's not the latent diffusion, right? It's not in like pixel space.
The equation with the gradient of P of x given y.
Yes, yes. So yeah, so in that case, we do not train the conditional diffusion model. So which means that we only train the diffusion unsupervisedly, so without the measurements to capture the distribution. And all the reconstruction or the conditional process is happening during the inference time. But definitely, I think for the current works, we have also seen the conditional diffusion with the Y in the training process, like the I2SB, the CDDB, and also including our works on based on the control net, we have the measurements in that one. So I think that definitely can compromise some benefit from such kind of the scheme, with the unsupervised training and also apply that. But I think people, in order to get the efficiency on the sampling time, inference time, people want to get this kind of trade-off. Yeah. And then for the second question, so I totally agree. It doesn't need, we don't need to limit the Y only to be the measurements. So why I call it as the measurements is because we, in this kind of context of the solving inverse problem in the medical imaging, but I should maybe use a better term as the condition or constraint, right? So for example, in the final works of the inverse design problem, so here, this is definitely not the measurements. So this is the desired physical property that we want to achieve there. And in order to do this, we're also using the similar idea, using diffusion as prior and using this kind of the posterior sampling process to solve that. But this is one of the examples that can be pretty generalizable. So this is also what I mentioned. Okay, we don't need to limit this only to the medical imaging, but the methodology can be pretty generalizable and flexible. Yeah, thank you.